11.4 more work with series. So we are going to further discuss a little more on series, on power series more in particular. So again, this is going to take us back to the different representations that we obtained in the previous section, this previous couple of sections. We're going to apply a little bit more of this, but in this case we're going to apply this in like adding functions like this, multiplying, even division, integration, differentiation, etc., or even composition. Well, we already did some of the composition to obtain new series in the previous section. And then, of course, as usual, the interval of convergence has to be considered for every new composition. Okay, let's do one more example in a very similar from the ones that we did. So find a power series for f of x equals x e to the x over 2. So here the most prominent part right here is the exponential part. How about we call it x e to the u, where in this case the u is x over 2. And then from here x sigma n equals 0 to infinity of u to the n over n factorial, and simply back substitute for the quantity u, which in this case is n equals 0 to infinity, so that's x over 2 to the n over n factorial. So in this case what you might want to do is distribute the power to the numerator and denominator of the quantity in parentheses. That is x sigma n equals 0 to infinity. That's going to give us an x to the n over 2 to the n divided by n factorial. But be careful, because you might want to rewrite this having the 2 to the n in the denominator, and there's something else I would like to do besides that. So 2 to the n times n factorial. How about introducing this x and multiplying with the x to the n? That's going to give us x to the n plus 1. So that'll be the series for the given function. And well, in this case, the u x over 2 doesn't have any restrictions. That means that we can we use the same interval of convergence, which is all real numbers. So interval of convergence, IOC for short. How about negative infinity to positive infinity? All right. So let's see. Let's look at another example. Number 1, write the first 4 terms of the series f of x equals e to the sine x by multiplying terms of the appropriate series. Well, so what are we going to do? Number 1, so in this case we have the product of e to the x times sine. So notice in this case we don't have a function like x cubed e to the x squared, for example, in which we develop a power series for e to the x squared, and we just introduce this x cubed inside of the sigma series. So now in this case we have the product of two functions that have particular power series. Well, how about, well, on the one hand, let's write their corresponding power series. E to the x, which is sigma n equals 0 to infinity x to the n over n factorial, and that's, well, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. Recall these 3 dots indicate that the series is it's an infinite series. And over here the same for sine x, that's sigma n equals 0 to infinity, that's a negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Alright, so in this case, developing the series, a few of the series, or expanding the series rather, that's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So a good way to memorize this series is the fact that The sine function, it's an odd function, and we only have the odd powers and the odd factorials. Alright? So now let's put these two together. So, well, let's see. So when we multiply e to the x sine of x, well, this will be the following. Well, number one, let me rewrite this series again. So I'm going to write 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth. I'm going to write one more plus dot dot dot. That times the polynomial expansion for the sine function, that is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the 9 over 9 factorial minus dot dot dot, indicate that this one goes on forever. Okay, well, so we are going to find a series for e to the x sine x by multiplying these two polynomials. Well, I know what you might be thinking. Does that look like a big hell? Yes, it is. So we would need to multiply 1 times every single term, etc. Right? And then once we're done, do the same with x times x times x cubed, x times x to the fifth, x times x to the 7. Alright? Or the same x squared over 2 factorial times each of these terms. Well, no. That's not how we're going to do it over here. Alright, we're going to take a different approach, and instead we're going to look for the possible products that give us the desired factor, or rather, not the desired factor, the desired power. Well, in this case, what's the lowest power possible when we multiply the polynomial expansion for e to the x times the polynomial expansion for sine x? Well, so here the lowest degree is 0, and here the lowest degree is 1. When we multiply these two together, the lowest degree possible will be x. Alright? So now the question is, so when we multiply 1 times x, that's x. So can you think of another way to multiply other terms so we get x to the first power? Well, so x, the next term, which is x, well, the next power will be x, that will be x squared. So no, there's no way we can get another power of x. So that's the first one. Now let's look for the square term. Well, number one, what if I multiply 1 times x cubed? No, that's higher. Okay, let's go with the second term, x times x. Well, that's going to be our x squared. Alright, is there any other way we can get that? Well, here we have an x squared over 2 factorial, of course. However, this gets multiplied with x and then x cubed, so no, that's not going to give us another x squared. Alright, now let's think of the cubes. And we need to be very careful here because, okay, number one, okay, let's see if we can get 1 times, oh, here it is, negative x cubed over 3 factorial, right? So that's one term. However, that's not the only possibility because, well, x times x, no, we already did that, that's x cubed. But how about x squared? Okay, so this is an x squared over 2 factorial times x, isn't it? X cubed over 2 factorial, yes. X cubed over 2 factorial. And let me put this together in parentheses, and then I'm going to simplify that. Alright, let's have a look at the x to the 4th power. So number one, let's see if we can think of something here. So number one, how about, well, this, well, 1 times x is x. 1 times x cubed is x cubed. Well, that's not going to give me a 4th power. How about this x? X times x we already did, but x times negative x to the 3rd power, that's going to be a 4th power, of course. All right. So let me open parentheses, negative x to the 4th over, in this case, 3 factorial. And how did I get that? By multiplying these two. this x times, right? Can I find another fourth power in a different way? Well, we have an x squared times x, that's x cubed, but x squared times x to the third, that's x to the fifth. No, that's bigger. Okay, so no, we need to think of a different way. How about the x cubed? Okay, x cubed times x, oh, that's the one. We can multiply with the x right here, and that's going to give us the what's that? X cubed plus x to the fourth, rather, over 3 factorial. All right, so notice in this case they're asking us for the first 4 terms of the series. So here that'll be the first term, second term, whatever we get from here will be the third term, whatever we get from here would be the fourth term. All right, do we agree with this? Well, so there is an issue here. Here, these 2 terms with the 4 powers, they are like terms with the opposite sign, so these are gonna cancel. So that's gonna leave me without that fourth, that fourth term. So in this case, I would have to go one more power, that is the 5th power. All right, let me open parentheses. Let me erase this. And well, so let's find a way to get the x to the 5th power. So number 1, if we multiply this one right here, okay, let me go back to colors here. 1 times x to the 5th over 5 factorial. So that's 1. Is there another way we can get that? Well, let's see. Okay, what about x? That's x squared, x to the 4, x to the 6. No. Okay, what about x squared? X squared times, oh, negative x cubed. Yes, that's going to do it. That's going to be minus, in fact. And so that's going to be x to the 5th. And be careful with the denominators here. Okay, let me point this out. So that's 2 factorial times 3 factorial in the denominator. And plus, okay, one more. Let's see if there's another way. Well, the x cubed times x, that's x to the 4th. X cubed times x cubed, well, that's x to the 6th. Well, no, that's not going to do it. What about this x to the 4th? X to the 4th times x. Oh, that's going to be an x to the 5th. X to the 5th and over 4 factorial. All right. And we're going to stop here because in this case, they're only asking us for the first 4 terms of the series. So I'm just going to I'm going to write a plus dot 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 to indicate that there's more terms. So again, be careful because these 2 cancel. They're the same quantity with opposite sign. And well, let's see. Once we combine these like terms, so that's e to the x sine x, e to the x sine x, so that's x plus x squared plus, okay, x cubed over 3 factorial and x cubed over 2 factorial. Once we combine these 2, that should give us x cubed over 3. And well, this combined to 0. And when we combine these 2 together, so let me just write the final answer to this. That's x to the 5th. 5 factorial, big number. 2 factorial times 3 factorial, another weird number. 4 factorial, big number. Compute this on a calculator. This should give us x to the 5th over 30 plus dot dot dot. Well, that's all we want, the first 4 terms of the series. And well, in this case, they're not asking us to write this in sigma notation, and in fact, don't even try, because the pattern is not very, very evident. It's not an easy one to figure it out. So all we're being asked right here is to use the polynomial multiplication. Okay, so let's look at example number 3. Find the first 3 non-zero terms in the Maclaurin series for f of x equals cosine squared. by using an appropriate trigonometric identity. So there's a few strategies right here. Number one, okay, you don't need to write this if you don't want, that's fine. I'm just going to do it right here. So f of x equals, well, it's a Maclaurin, that means center a equals to 0. So, well, cosine squared of x and f prime of 0, cosine 0 quantity squared, which is, well, cosine 0 is 1, 1 squared is 1. Take the derivative right here, okay? Take the derivative, that's 2 cosine x sine x times actually negative, because the derivative of cosine is negative. There's a mini chain rule, and then see how this is going to start complicating. Negative 2 times cosine 0, cosine, or rather sine 0. Well, this is going to be 0. Now take the second derivative. Well, second derivative, see how it's already, it requires a product rule. So no, I don't think this is a good way to get the, the power series right here. All right, another way it would be, okay, f of x equals cosine squared. That's the same as cosine times itself. And then, well, this is going to be, well, I believe this one was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot dot dot, well, and then multiply by itself. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot dot dot. And well, we already saw how messy it is to multiply polynomials this way, right? So no, we're not going to take this approach. So that's why in this case, in the instructions right here, they're specifying to use an appropriate trigonometric identity, and trust me, this is going to be a lot better, a lot easier and shorter. Well, so let's go about that. F of x equals cosine squared x, and you might remember this identity from power reduction formulas when we covered trigonometric integrations. Okay, let me rewrite this as 1/2 plus 1/2 cosine 2x. Okay, and then I'm going to go back and rewrite this cosine 2x as 1/2 plus 1/2 cosine of u, where in this case, as usual, the u will be taken by the quantity 2x. All right, so from here then, well, so you might want to use a power series for cosine of u. So that's 1/2 plus 1/2 sigma n equals 0 to infinity, and that's a -1 to the n u to the 2n over 2n factorial. And we'll go back, substitute for u, that's 1/2 plus 1/2 sigma n equals 0 to infinity, and well, this will be -1 to the n, that's a 2x to the 2n over 2n factorial. Alright, so for now I'm gonna leave it like this. I know technically I'm supposed to write this 2 to the 2n and x to the 2n, but I'm gonna leave it like this because ultimately what we want is it's a polynomial. So I'm gonna leave this 2x instead like this, and then I'm going to rewrite this in terms of a polynomial series. So that's 1/2 plus 1/2 times. For n equals to 0, that's a positive, that's a 1, and then 2 times 0 is 0, 2n factorial is also 0, 2 times 0 factorial, well, that's 0 factorial, which is 1. And well, the next term for n equals to 1, that's going to be -1 to the n, that's a -1 to the first, that's a -1. And then 2x, let me write this as a 2x to the 2 times n, which is 2 times 1, that is 2 over 2 factorial, and then plus 2x to the fourth over 4 factorial, and then following this pattern minus 2x to the sixth over 6 factorial, plus just continue the pattern. Okay, well, that'll be this one right here. Alright, so let's just continue simplifying this. Well, what I would like to do first is I'm going to distribute this 1/2 and so that's 1/2 plus 1/2 minus 2x, so that's going to be the 2 squared x squared over 2 times 2 factorial plus 2 to the fourth x to the fourth over 4 factorial, but don't forget the multiplication by 1/2, which is going to be this one, and then minus 2 to the 6 x to the 6 over 6 factorial times 2, alright, plus dot dot dot. So when we combine this half plus half, that is going to be a 1, and 2 squared over 2, that's going to be a 2 over 2 factorial, 2x squared over 2 factorial, which technically cancel, plus 2 cubed x to the fourth over 4 factorial minus 2 to the fifth x to the sixth over 6 factorial. And of course, I mean, you might want to just simplify this quantity. For now, let's leave it like this. All right, all on the homework, you might be asked for simplified version. Just simplify the coefficients using a calculator. All right. Let's do one more example. Okay, find the power series for f of x equals cosine of the square root of x. Well, which we already did something like this in the previous section as well. However, this exercise, it's going to be very, very interesting. Well, you'll see why. So, on the one hand, okay, let's start writing the function first. F of x equals cosine of the square root of x. Well, in this case, if we write this in terms of u, cosine of u, where in this case the u equals the square root of x. This means well, we can write sigma n equals 0 to infinity and use the power series for the cosine function. And in this case, the power series for the cosine function, we already I believe we already used it before. Yes, we did. And u to the 2n over 2n factorial. Alright, so in this case, well, let's see. We can just go back, substitute for sigma n equals 0 to infinity, negative 1 to the n. That's the square root of x times, or rather to the 2n power over 2n factorial. And well, notice how in this case the square here cancels the radical, leaving us with the following: simply sigma n equals 0 to infinity. That's going to be negative 1 to the n x to the n, the whole thing over 2n factorial. Be careful with having all parentheses around. All right. So for this series, well, let's discuss the interval of convergence. I know, yes, so your initial thought right here is the fact that yes, interval of convergence for cosine is all real numbers, negative infinity to positive infinity. However, I mean, this is what would you get if you did the ratio test and find the radius of convergence. In this case, I will leave you that as an exercise to do the ratio test on the series, and you will find out that r will be infinity, because you will find out that the limit will be 0. And recall that when the limit is 0, that means that the radius of convergence is infinity. Because yes, you don't have limit is 0 means you don't have limits, you can go anywhere. So that's what this series can do, converge anywhere in the real number line. However, be careful with the function that we are dealing with. This is not going to be true for this, because in this case we're dealing with, oh come on, we are dealing with a composition involving square root of x, and this function has restrictions. All right, can we plug in negative numbers, like this? No. So the interval of convergence then will be for this from 0 to infinity. All right, so be careful when you see something like this. In fact, you know what this symbol means, that's one of the typical exam questions I like giving. All right, so what else can we use power series for to compute limits? Well, of course you can compute this limit, okay, so it's e to the 0 minus 1 over 0, that's 1 minus 1 over 0, 0 over 0. Well, that's an indeterminate form. You could easily use the L'Hopital's rule for this one. However, we are going to take the power series approach in this case. And to do that, well, let's go ahead and write this into, let's focus on the exponential function, that is the elementary function that we have in the limit. This will be the limit sigma n equals 0 to infinity of x to the n, simply x to the n over n factorial. Nothing crazy for the u, because this is simply e to the x. Recall that if it were something like e to the x squared, e to the x over 2, well, then we take that as a composition. All right, that minus 1 over x as x approaches 0. So this is what we're going to do. We will expand a few terms of the series for the exponential function. So that's a limit of 1 plus x, plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. Well, that's enough. And then don't forget this minus 1. And then the whole thing over x, as x approaches 0. Well, this will be the limit. X approaches 0. Okay, this is a 1 minus 1, so these ones are going to get cancelled. All right, cancel this one with that negative 1, and we will be left with the following. We will be left with x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot 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 over x. So now in this case we can divide every term in the numerator by x, and that's going to leave us with limit x approaches 0, and that's x over x, that's going to be 1. X squared over x, that's x over 2 factorial plus x squared over 3 factorial plus x cubed over 4 factorial plus dot dot dot. Notice this dot 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 implies again infinitely many terms involving x. Now what's going to happen when you evaluate the limits for all these x terms? Well, you guessed it right. We're going to go to 0, 0, 0, etc. infinitely many times. And the only term that really survives right here is going to be this one right here. So the limit is 1. The same way that if we did it using the L'Hopital's rule. Let's do another limit. These are fun to do. So for this limit expression, let's see. So number 1, this is the limit x squared plus 2 times the series for cosine, in this case it's nothing crazy, nothing fancy, just -1 to the n, x to the 2n, no compositions in this case like before, over 2n factorial, and then -2. The whole thing divided by x to the 4th power, and then in this case as x approaches 0. So let's go ahead and do this one. Okay, so limit x approaches 0, that's an x squared plus 2 times the series expansion. Let me write it in polynomial form, just a few terms. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot 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 and -2. Alright, so what's going to happen here? Well, number one, so I'm going to distribute the whole thing over x to the 4th power. Okay, so I'm going to distribute these two. Alright, and this will be the limit x approaches 0, so that's going to be x squared plus 2 right here, and then minus 2x squared over 2 factorial. Do we agree that these two cancel these 2 factorial because they're the same number? And then here I'm not going to expand the factorial, I'm just going to leave it the way it is. I'm just going to write it as x to the 4th, or rather 2x to the 4th over 4 factorial minus 2 x to the 6th over 6 factorial plus dot 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 minus 2. And then the whole thing over x to the 4th power. So on the one hand, see what's going to happen. Number one, these 2's are going to cancel, and on the other hand, this x squared is going to cancel with that x squared. By the way, I needed a plus sign here, right, to denote addition. And well, we're going to be left with, in this case, yes, limit x approaches 0, so that's 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus etc. over x to the 4th, which in this case will be, see how in this case the x to the 4 over x to the 4th cancel, that's limit simply 2 over 4 factorial minus 2x to the, x to the 6th divided by x to the 4th, that's going to be x squared over 6 factorial plus infinitely many terms involving x, but in the just like in the previous example, this one goes to 0, whatever term is going to go to 0, etc., etc., because these are all terms involving 0, and in this case the limit that we're studying in this case is as x approaches 0. So we're going to be left with 2 over 4 factorial, which is 2 over 24, which reduces to 1 over 12. Alright?